All right, today I will be talking about NAND gates. NAND is short for not and, or inverted and. So to do a quick recap, the not looks like a triangle with a clown nose. Whatever it has one input, one output. Whatever on the input is inverted on the output. So if you feed it 1, it becomes 0. If you give it 0, it outputs 1. Well, in the case of AND, the AND gate looks like a letter D, capital D, with 2 or more inputs and 1 output. It needs all inputs to be 1 for the output to be 1. Otherwise, it outputs 0. So the truth table looks like the following. When A and B are 0, outputs 0. When A0, B1, output 0. When A1, B0, output 0. When both of them are 1, output 1. The NAND gate pretty much looks like this. It's an AND gate with a clown nose and your usual input and output. The NAND gate is just like an AND. It takes 2 or more inputs and has 1 output. The not only 1 input, 1 out. The AND 2 or more and inputs, 1 output. The NAND 2 or more inputs, 1 output. If you want to look a little bit deeper on the inside on how this actually looks like, not transistor level, like I just want to show you how it, how this looks when we break it down to not an AND. It looks like this. We have an AND gate fed into a NOT gate. A, B. So the stuff in the dotted line, these AND and NOT gains in the dotted line, are the equivalent of this one symbol here with the clown nose. That's exactly how it works, how it functions. It's pretty much an AND gate whose output is fed into a NOT gate to get the, the results on the output. So let's try to understand the truth table for this bad boy. And to understand the truth table, I'm actually going to use this circuit at the bottom. Okay, so not and, so and into not, boom, boom, boom. Here, I'm gonna name the output of this AND gate. I'm gonna give it like a temporary name. Let's say call it K. Okay. Now let's set up our truth table. A, B, K, Y. Now remember, how many cases in the truth table depends on how many inputs we have. So we have 2 inputs, right? Binary, 0 and 1. So you have 2 inputs. The number of cases, it depends on how many inputs we have. So it's going to be 2 to the power of n, where n is number of inputs. 2 to the power of 2 is equal 4. So we have 4 cases. We used to go case 0, 1, 2, 3. So case 0 is going to get represented as 0, 0. Case 1, 0, 1. Case 2, 1, 0. Case 3, 1, 1. This is 0. This is like 0 in binary. This is 0. This is the first one is 0 in binary. The second one is 1 in binary. The third one is 2 in binary. The fourth one is 3 in binary. Let's start tracing the inputs and the outputs and document our finding under columns K and Y. You're going to start 0, 0. So when A is 0, B is 0. When an AND gate receives 2 zeros, If you look at the right side, 1, 2 zeros, the output is 0. Now, when this goes into the NOT, it gets inverted to 1. Cool. Now, let's look at the second case where A is 0, B is 1. Remember, the AND gate needs all inputs to be 1 for it to process 1 or give you 1 on the output. Otherwise, it's still 0. So in this case, A is 0, B is 1. If you look at the right side, A is 0, B 1, the output is 0. So we have a 0 here. This 0 goes through the NOT gate. It gets inverted to 1. Next, we're going to look at this here case where A is 1, B is 0. A1, B0. 1 and 0 is going to be 0. It gets inverted on the output. It becomes 1. Right? I'm sorry. I forgot to do this. Hold on. Wait a minute. All right. Now for the final case, let's give it a gold, When A is 1, B is 1, the output of this and the AND gate is going to be 1. But that one gets fed into the inverter, the NOT gate, and it becomes 0. Okay. We know that the K here is going to be the output of this AND gate and output, while the Y is going to be the output of the NAND gate because it has to pass through AND, then NOT to obtain the output Y. So we're going to call this NAND output. Now let's look at the values. We said that the NAND gate is an inverted AND. So let's verify that. When both A and B are 0, the AND outputs 0 and the NAND outputs 1. When A is 0 and B is 1, AND outputs 0, NAND outputs 1. When A is 1, B is 0, AND outputs 0, NAND outputs 1. For the last case, when A and B are 1, AND outputs 1, however, NAND's output 0. So look at it. Whenever AND is outputting 1, NAND is outputting 0. And whenever AND is outputting 0, NAND is outputting 1. So there you have it. So to summarize things, the NAND gate looks like an AND with a clown nose that has 2 or more inputs and 1 output. The NAND gate behaves in an opposite fashion to the AND, and its truth table is the following: A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0. Algebraically, this can be expressed as the following: Y equal A and B inverted. Or this can be written in another way, like the following: AY equal A and B inverted. You can use the apostrophe or the bar, which means not. There you have it.